TV. Okay, and as this is at point A, we are taking A. Okay, so TVA. So what it will be if this is T. Now see that if this is the tension, suppose this is the tension that is acting along the tangent, right? So this is x-axis, so this is theta. So the transverse component will be t sine theta. So I hope everybody gets that. So if this is t acting in this direction along the tangent at A, so the transverse component or the vertical component will be t sine theta, right? So that's why I am writing it t sine theta. Okay. Now, as theta is very small, as I told you that we have given a very small displacement along y-axis, right? So that's why theta is very small. So when theta is very small, we can write sine theta is almost equal to tan theta. Okay. Why? Because theta is very small and tan theta equal to sine theta by cos theta. So cos theta tends to 0. It is 1. So that's why sine theta is almost equal to tan theta. And tan theta, you know, is del y del x. That is the slope at A. Right? So we are going to put the value of this sine theta at this equation. Suppose this is our equation 1. Okay. So the transverse component of t at point A is given by t del y del x. So this is our equation 2. So similarly, the transverse, if we want to calculate, so what we will do? We will calculate the tension or the force that is acting at this point B in the transverse direction. So we will take the transverse component of the tension at point B. So let me write it down. The transverse component of T at B, at point B. So let's write it down it as TVB. So this is V stands for vertical and B as this is calculated at point B. So we are going to write down following the equation 2. So T and then del x. Now for point B, as you can see over here, for point B, the value of y is y plus delta y. So we are replacing y by y plus delta y. Okay. So if I do that, so it is basically, can write it down as t del x y plus del y del x into delta x. So this part, what I have written over here, so basically I have written delta y as del y del x into delta x. So this part comes from the definition of partial derivatives. You know, if there is a function f, which is a function of suppose x, right? So we can write down the total change df or delta f, whatever it is, df can be written as del f del x into dx. Okay, so this is the rate change, this is the rate change multiplied by the total change, right? So this will give you the total change in f. Okay, so similarly, applying this formulation of partial derivatives, I have used this formula, delta y equal to del y del x, the rate change multiplied by delta x. Okay, so that's why we have written it like this. Now, what we are trying to calculate, the force on this particular AB string, right? So you can see that if, we have already calculated what is the transverse force acting on point A and what is the transverse force acting on point B. Obviously, this is along this direction and this is along this direction. So basically, they are opposite to each other. So we will just take the difference between them and we will get the resultant force that is acting on the element AB. So let's calculate the force then. So the resultant force on AB, so basically the difference between these two components. Okay. So if I write down the expression, it is T, so this is equation 3. So it is T del x y plus this del x, then y plus this and minus TVA. What is the expression? T del y del x. So T del y del x. So you can see this T del y del x terms, this cancels out and we get this term to delta x. So this is the total force that is acting on the element. So where we have started, we wanted to write down the equation of motion of this string, and you can see we have calculated the right hand side part, that is the force acting on the string, and now we have to write down the left hand side part, which is the mass into acceleration. Okay, so this is our expression of force. So this is our force. So let's number this as equation 4. So now mass into acceleration. So about the mass, if m is mass per unit length, okay, of this element AB, so the mass per unit length when it was not struck, okay, so when it was in this position A1 B1, the mass per unit length, it was given by m. Okay, so what will be the total mass of this element? So m into length of the element, right? So it is m into delta x. So is it clear to everybody? So if there is no doubt, we can move on. So the total mass of element AB is given by m, mass per unit length, into the length. Okay, this is the mass. And what about the acceleration? So acceleration is in y direction. So it is basically del square y into del t square. Okay, so we are taking only y direction. So y is the displacement along our transverse direction. So now we are in a position to write down the equation of motion. So equation of motion of AB. So mass is m into delta x multiplied by the acceleration in transverse direction, that is del square y del t square, and this is equal to our net force. And this is the expression, equation 4, T del square y del x square into delta x. T del square y del x square into delta x. So this delta x cancels out from both sides, and we can write down del square y del t square is basically t by m del square y del x square. Okay, so this we can write down as del square y del t square is equal to c square del square y del x square. So C is root over T by N. So now can you recognize this equation? This is the wave equation in one dimension. Okay, so this is the representation of wave equation. This is a very famous equation, just like the SHM equation. It is also a very famous equation. Right. So is this correct now? I hope so. And this is 5 and this is 6. Right. So this is a very famous wave equation. This is wave equation in one dimension. So basically, if you forget if it is c square or it is 1 by c square, okay, so just you take the dimensional analysis of the equation. That means the dimension of the left hand side should be equal to the dimension of the right hand side. So you can see if I take this c is basically length by time squared, and this has the dimension 1 by length squared, this has the time 1 by time squared. So it cancels out, and then this 2 has the same dimension, this right hand side and left hand side part, right? So that's why that's how you can remember whether it is c square or 1 by c square in which side. Okay. And just look at the expression of c over here. So what is c? C is the velocity of the wave, transverse wave, that is going to propagate when we struck the string, right? Or we pluck the string. So what are the parameters that this wave velocity depends on? The first parameter is the tension that we are putting onto it, right? So if we are giving T tension, so the velocity of the wave will depend on this tension and the mass per unit length. Okay, so it will depend on mass per unit length. Please note that this velocity, whatever velocity it will attain, it does not depend on the length of the string. Okay, whatever may be the length of the string, this velocity does not depend on it. It depends on the whole mass. What is the whole mass of the total mass of the string? It depends on mass per unit length. Okay. So that's all. So this is our wave equation. We have arrived at our wave equation. We have the expression of the velocity of the wave. Now it's time to write down the solution of this equation. I hope the solution of this equation you have already already had the class that how it can be solved like this. Okay, and it can have solution like this, ct plus x or ct minus x. So the general solution of wave equation. So let me write down over here. This is wave equation in 1D. Okay. So the general solution can be written like y, the displacement, is a function of either ct minus x or some function of ct plus x. Whether it will be ct plus x or minus x depends on the direction of the wave, whether it is propagating along the x-axis or opposite to the x-axis. Okay, so it is, we don't know that in which way this wave is propagating. So that's why we have combined this these two solutions over there, and we have written the general solution of it. Now this is in general, this is for transverse vibration of our string, but in general the wave equation that we got in 3-dimensional, how it looks like. Okay, so I am writing the form. It is very easy. It is del square y del t square. It's not going to change, and then c square, and only this part del square y del x square is going to change, because for a 3-dimensional case we will have 3 coordinates, so that's why the this will change as del square, or let me write down as psi. Okay, psi del square psi. Now you will ask, ma'am, why you are writing this y as psi? So basically we are taking here, this y here is the displacement that we have taken in the transverse direction, right? But here you can see psi is the displacement. Okay, so we are taking psi is the displacement. Okay, so I have written psi, just you don't confuse with the coordinates, okay? Because in del square, there are del square, del square has this term. It is equivalent to del square del x square plus del square del y square, and del square del z square for rectangular coordinate system. Obviously for spherical and cylindrical, it it changes its expression. This formulation will change, so just that you do not হ্যাঁ বলতে পারবে না, কোনো ফাংশন সাই, এখানে y এর জায়গায় সাই ফাংশন বলো, কোনো অসুবিধা নেই। বাট ইট ইজ ডিসপ্লেসমেন্ট অ্যাট, মানে কি বলতে চাইছে, মানেটা কি, মানে ফিজিক্যালি তুমি কি বুঝবে সাই হিসাবে? সো দ্যাট ইজ অ্যাট পয়েন্ট টি, at no, in space, suppose you are looking at some space which is at position x. Okay, at position x at time t, the displacement of the particle will be psi. That's the physical meaning of it. And now you want to call it displacement, want to call it wave function, it's up to you. Okay, so this is the what physically it means. Okay, so that's yes.
Ma'am, basically we are trying to reach the Schrodinger's wave function, right?
No, a Schrodinger wave function is basically for quantum mechanics. We are strictly in the classical.
Okay.
Okay. So quantum mechanics is for atomic region where the there are certain things, that certain criteria is there, right? So that has to be fulfilled. We are not reaching there, but yes, Schrodinger equation sometimes behave like wave equation, and it has wave equation like solutions, but that has to be discussed in your quantum mechanics class. That will be in your next semester. Okay, so till now we are strictly in the classical regime. We are not considering the quantum regime. Okay, so it is basically whatever this equation actually represent, whatever you do with your guitar. I hope some of you might play guitar or piano or something, some musical instrument. I hope so. So this is also wave equation. Okay, so don't this is very simple. This is classical region. Okay, so the next thing we want to do here, one thing I want to tell you, that this del square nabla square operator, I hope you all know this, right? Can anybody answer? Del square, you have vector analysis class, right? You know the representation. Okay, quite good. Okay, so that's the 3D wave equation. Right, so the next thing we want to discuss, that is the general solution of this wave equation, and we will apply the method of separation of variables. This method of separation of variables is a very strong tool to be learned. Okay, it is a very useful tool, and in my research also, when I was doing my research, I get a very complex differential non-linear partial differential equation, and I solved it by using this method of separation of variables. Okay, so it's very helpful method, and you will, you will encounter it in various parts of your syllabus. Okay, especially in quantum mechanics you will apply it. So let's see what is a method of separation of variables. I think that you people know, but we will do this for our wave equation. So general solution, this topic is general solution of the wave equation, and this is a method of separation of variables. So let's write down the equation first. This is a very easy section. So this is our wave equation in 1D. And y is a function, y this displacement, as contrary to our oscillation where y, the displacement, was only function of time. Now we can see that it is function of both x and t, that means position and time. So we are going to assume the solution, okay, such that suppose f1, we are taking f1, a function which is only dependent on x, and we are taking f2, another function which is only dependent on t. Okay, so the solution, the y solution, is actually the, you just multiply f1 and f2, you will get the solution. Okay, so that is the thing that we have considered. Now let's just so this is our equation 1, this is our equation 2. So we will put the value of y in our equation 1 and see what happens over there. So see, del square y, in place of y I am writing f1 and f2. y এই যে এখানে লিখেছি x and t, x না না, এক নম্বরটা হচ্ছে আমার ডিফারেনশিয়াল ইকুয়েশন। দিস ইজ আওয়ার ডিফারেনশিয়াল ইকুয়েশন। এবার এই ইকুয়েশনটাকে সলভ করতে গেলে এটাকে আমি অ্যাজিউম করে নিচ্ছি, যেমন তোমরা করো যে সাপোজ একটা ডিফারেনশিয়াল ইকুয়েশন আছে, সাপোজ এক্স ওয়াই ইকুয়াল টু ই টু দি পাওয়ার আলফা এক্স, দিয়ে আবার সেটাকে পুট করো ডিফারেনশিয়াল ইকুয়েশনে, দিয়ে আলফার ভ্যালু বের করে করো না, যেমন করেছিলাম ড্যাম্পড অসিলেশনে, ফোর্সড অসিলেশনে। সিমিলারলি সেরকমই আমি একটা সলিউশন অ্যাজিউম করে নিয়েছি। ঠিক আছে, এটা হচ্ছে আমাকে সলভ করতে হবে, আর এটা হচ্ছে আমাকে অ্যাজিউম করেছি আমি। ঠিক আছে, আচ্ছা এবারে দেখো, আচ্ছা সো দিস ইজ দিস, and then let's put c square. So del square f1 f2 del x square. Now see, this is partial derivatives, right? So f1 is a function of x only, so this del square del t square will not act on f1. So I can take this out, f1, and I can write it's only del square f2 del t square, right? Because f1 is only function of x, right here. And again here you can see this is del square del x square, so it will not operate on f2, which is only function of time. So we can take f2 out of this derivatives, and I can write del square f1 into del x square. Okay, so now what I will do, I want to write down this equation in such a way that our left hand side is a function of t only and right hand side is a function of x only. Okay, so we want to separate the variables. That's why the method is called separation of variables. So I am going to, so how we can do this? You see, f1 sitting over here is a function of x. So I am going to divide it by f1, and here f2 is a function of t sitting with x. So I am also going to divide it by f2. So actually what we are going to do, we are going to divide this last equation by f1 and f2. So if I do this, I will get 1 by f2, then del square f2 del t square, then c square, then 1 by f1 del square f1 del t square, right? So see, now this function is all, this part is only a function of t, this part only function of x. So I can write this is equal to this, these two parts are actually equal to some constant, and I am taking this constant as minus omega square. So I hope you understand this method now. This is a function of t only, and this is function of x only. The only way they can be equal for every possible x and every possibility is that they are constant. Okay, so that's why I'm taking it, they are equal to minus omega square, some constant. So moving on, now we get we get two equations from our last equation. One is, you can see, this is equal to minus omega square, and the other equation is this is equal to minus omega square. So let's write down the equations of here. So basically d square f2 d square plus omega square f2 is equal to 0, and the other equation I get d square f1 dx square plus omega square by c square f1 is equal to 0. Can anybody tell me that I was writing del up to this equation, and now I am certainly suddenly I am starting to write d from this equation. Why this is so?
কারণ ম্যাডাম f2 শুধু t এর উপরই নির্ভর করছে, ফাংশন শুধু।
রাইট, কি নাম গো তোমার?
ম্যাডাম শুভঙ্কর। ম্যাডাম
শুভঙ্কর, ভেরি গুড। কারণ এই ইকুয়েশনে আর কোনো ফাংশন নেই, তাই তো, f2 শুধু t এর উপর, এখানে f1 শুধু x এর উপর। তো দেখো, so this equation actually resembles our equation of SHM. Okay, so these are if I want to write down the solution, we already know the solution, right? So the solution for f2 is c1 cos omega t plus c2 sin omega t in general solution, right? We all know this. And for f1 we can write just omega will be replaced by omega by c, right? So it is some other constant d1 and then cos omega x by c plus d2 sin omega x by c. Okay, so c1, c2, d1, d2, they are constant, and how we can find them? We can find them by the initial and boundary conditions. So the final solution we can get is y equal to f1 into f2 c1 cos omega t plus c2 sin omega t multiplied by d1 cos omega x by c plus d2 sin omega x by c. So this is our in general solution, but please remember that this solution, the form of this solution will vary depending on the system we choose. Okay, so the value of C1, C2, D1, D2 will change, and according to which our main displacement, this main solution Y, that is going to change. Okay, so in our next class we are going to see a particular example, that is stationary waves, and we will take this general solution to see that what happens when this stationary wave is formed, how it is formed, and how we can find out these values of C1, C2, D1, D2, applying the initial and boundary conditions. So that's all for today. So let's take your attendance.
Ma'am, the value of C1, C2 and D1, D2, ma'am, they change. The equations means the system will depend on the values of C1, C2 and D1, D2.
Obviously,
Means it is system specific. If I change the system, the values will also change.
Obviously, the values will also change. And not only that, if you take the same system and apply different initial or different boundary condition, you will get different solution. You will get different waves, different kind of waves or solutions. Okay, so that has to be noted. Suppose তুমি ধরো গিটার বাজাচ্ছো, তুমি যদি টিউন করো বা টিউন না করো, যেমন ভাবে তুমি প্লাগ করবে সেরকম তোমার টিউন আসবে, তাই তো? তাহলে তুমি গিটার তো আর চেঞ্জ করে দিচ্ছ না, তোমার সিস্টেম তো, তাহলে তুমি ডিফারেন্ট ওয়েভস কিভাবে ক্রিয়েট করছো, ডিফারেন্ট সলিউশন। তো সেরকমই, মানে পুরোটা এক হলো না, এটা জাস্ট অ্যান এক্সাম্পল হিসাবে তুমি নিতে পারো। বা ধরো তুমি একটা সিম্পল মানে